Hi folks, Dr. Shane here. Kind of starting this video from behind the camera. I think I'll come out in front now. I'm making these videos on Monday of week 2. Cumberland County just received sort of a no unnecessary travel award, so I'm making these a little bit earlier than I thought I would, so maybe they're not going to be quite as coherent because I'm doing them kind of quickly here because as of 8 o'clock this evening of my video is we're not supposed to be out and about. I think we'll be okay. So we're fast forwarding in time here, getting in the time machine of YouTube, and we are at the beginning of week 3. This actually should be a really straightforward week to be organized. All we're trying to do this week is finish chapter 13 on equilibrium. Chapter 14 is also equilibrium, but specifically for acids and bases, and pH and buffers and all this good stuff. We'll get to that. I think we're just going to keep it simple right now. We're just going to finish chapter 13, which really means a few things in concrete fashion. We want to finish section 13.4. We're maybe halfway through 13.4 at this point with problem set number 2 and all those videos from last week. And then we want to do problem set number 3, which has some pretty challenging problems in it. So this is going to take some time. Okay, so we want to finish those, and then we'll take a quiz. So those are really your tasks for the week. That's fine. So is to finish that, problem set 3, quiz, those are your things you want to do. So I'll give you a second here to get warmed up, get ready to go. I'm still using the slides from chapter 13. In fact, I've got my computer right here. So we are on number 3 on the slides. Which slide is this? That's slide number 7. So we're on slide number 7 of the slides we've been using for quite some time. Excuse me. Okay. So I'm using an abbreviated heading here. So what kind of calculation are we doing? So if you're given a KEQ, so you have a numerical value for KEQ and some initial concentration, our goal here is to find the equilibrium concentration for all reactants and products using the ICE analysis. Initial, change, usually we use an X for that, and then equilibrium. So we're going to do that ICE analysis, which we kind of talked a little bit about, but we really didn't do a ton of math. Okay. I mentioned this on the slides, but I didn't write them down because I wrote these down by hand. So if you actually want to, I'm going to go through these, but you may want to stop the video and just copy these down. Your book does a great job. I know I always say that, but I think your book does a really good job with these calculations. It's not the beginning of section 13.4. Scroll down to find a heading like this, calculating equilibrium concentrations from initial concentrations, I think is the heading of the book. And you'll see that they give you 4 general steps to do all of these problems. Now, they're harder than they seem. So I wrote these steps a little bit differently than your book did. I wrote them as 2 questions, I guess. So these are general steps that are going to take a little while to apply. But the first question is, which direction, based on the initial concentrations, does the reaction need to go to reach equilibrium? So if you're given an initial concentration of a reactant, well, it has to shift towards the product side. If you're given the concentration of a product, well, it'll have to shift towards the reactant side. Okay, so just to satisfy which direction, shift right or shift left with Chateliers, does it need to go? What changes are needed? What does that mean? Well, that's the C part of the ICE table, and that's where we use an X. Either a plus X if the concentration has to go up, or a minus X if the concentration has to go down. And the only caveat there is what goes in front of the X. If there's a coefficient of 2 in front of the chemical, it'll be a 2X. So plus or minus, or if the coefficient is a 5, it'll be a plus or minus depending on which direction. A 5X, so just to let you know what change is necessary based on also the balanced chemical equation. This step is the big one. Set up the math. KEQ equals. And it'll be a bunch of X's and a bunch of, okay. And then we're going to make some assumptions about X. Is X really big? Is X really small? Those are some assumptions we can make that will make our life easier. Sometimes we can't make those assumptions and have to do math the long way, oftentimes using the quadratic equation, which we're going to have to remind you how to do that. Okay, so that's the big one. This is the one that's going to take a little while. So you solve for X, go back and calculate all your equilibrium concentration, and you've answered the question. Then you actually, in many cases, know that if you've done the problem right, is if you recalculate KEQ using all these equilibrium, you should get the same answer. So this is self-checking. Now, these steps might not make a whole lot of sense in the abstract. You need to see some examples. So, but that's a good set of things to look at, to write down, and to come back and refer to as we do these problems. So if you want to take some time and stop the video, copy those down, think about it for a second. Now I'm going to show you some examples. And I think I'm just going to show you one example in this problem, and then we'll maybe do some other ones so the videos aren't too long. And what I'll do this week essentially is put a checklist of problems that you can do. Okay, so stop the video if you want to. I'm just going to erase all this stuff. I don't think we need anything else because I need all this space. Oh, by the way, I hope you like my t-shirt. It's my science t-shirt from chemistry camp a couple of years ago. Somebody gave me. I kind of was in a hurry to get up here to make videos, so I didn't get very well dressed. Okay, and you can already copy down the answer. Sorry, the question we're doing is on the slides. Is example of ice tables. And it's example number 1 from the slide. So if you want to copy that down, I'm not gonna copy all of that down. So it's number 1. It's what is this? Acetic acid. We've talked about acetic acid already, and there are 4 parts: A, B, C, and D to the problem. So if you want to copy down the original problem in your notes, go ahead and do that. I'm going to solve that with you. So you'll need a calculator. As usual, I'll set up some math and give you a chance to solve it. Okay, so this is example number 1. And there's actually different ways of writing the chemical formula for acetic acid. It is a weak monoprotic acid. Fine. So it's weak and monoprotic. And sometimes the symbol we use is HC2. H3O2, that's the symbol I'm going to use. I may have mentioned this before. Those are 3 different ways of writing this. This shows you this is the hydrogen that's lost to form H+. In this formula, this is a better formula actually, and this is a super abbreviated, the acetate ion and then the H+ that is lost. This is one that's often used in lab just for simplicity's sake. Okay, so write the equilibrium chemical equation. We've done this one already in various contexts. This is a review. It's not H2. This is a homogeneous aqueous equilibrium with a monoprotic, it gives off 1 H+, weak acid. Fine, so this is homogeneous aqueous. Might as well do the problem like it is. What is the appropriate equilibrium? Okay, we've done this already. Oh, by the way, when we get into the next chapter, yeah, this is a KC, but since we're going to talk about acids and bases so much, this is often called a Ka. An acid, it's called an acid dissociation constant, so specifically for acids. So just keep that in mind for later. For this problem, it doesn't really matter. It's an equilibrium constant. And that would be products over reactants, like always. And I'm not going to bother with the AQ subscript at this point. equilibrium constant expression, that's kind of new. And then I think it says, what else? Derive the units. Well, molarity times molarity divided by molarity. Well, the units are going to be molarity because one of the molarities is going to cancel. It doesn't really matter which one. Leaving you, okay, so the units are going to be molarity. Fine. Part C, I'm going to have to erase this. Based on the magnitude size of K, does it make sense that acetic acid is weak? Well, you're given the fact that Kc, or Ka, is 1.8 times 10 to the minus 5. What does that mean? That's a pretty small number, isn't it? That means that this denominator is really big compared to the numerator. You're only going to get a small number. That's really, really big. What does that mean? That means that most of acetic acid stays in the undissociated form. That very little of it dissociates into these two. The fact that it's really, really small, another way I guess of saying that's really, 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 really less than 1. Most of it's undissociated. Okay? Well, what does that mean? That's the definition of a weak acid. A weak acid doesn't dissociate very much. That's exactly what it is. And acetic acid is the classic example. What does that mean mathematically? I'm going to show this later. That means that not much goes this direction. Our x, our change going from initial to final, will be very, very small. And that's an important assumption. That third step, make some assumptions about x. This is the one we make for this problem. X will be really, really small in this case. Okay. And the last one is the actual problem. Assume we have an initial concentration of 1 molar acetic acid. So the initial concentration here is 1 molar. So the reaction is going to have to go to the right, because the initial concentration here and here is 0. Well, let's set that up. And I'm going to not erase everything, because I'm going to use this equation, and we'll set up an ICE, an ice table, right underneath this. Yeah, we're going to need all this later, but not recommended. I don't need to do all that now. So this is now part D. Okay, so we do our initial change, equilibrium, and keep in mind all these are molarities. I don't want to have to keep writing and molarity. They're always molarities. And in this particular problem, we're keeping it simple, so we keep the math simple. Start off with 1 molar of this. The initial here is 0. Fine. Well, this is going to have to go down by some amount, and these two are going to have to go up by the same amount. Every coefficient here is 1. So this one's pretty easy. This is going to go up by x. Every time we make an H+, we make the exact same amount of acetate. That's going to be plus x. And this is going to be minus x. Then you just add the columns up. So this is equal to 0 and plus x. Well, that's pretty easy, isn't it? Okay, so we're trying to solve for x. So here's the general idea. You set up your ice table. You solve for x, setting it equal to k and q, which we'll do in a minute. And then the final step is to come back and calculate the equilibrium concentration. So what's the equilibrium concentration of H+? It's equal to x. The equilibrium concentration of acetate is equal to x. So you're solving for the same thing. For acetic acid, it's 1 minus x. That's all there is to it for this problem. They get a little more difficult. and I think I'm going to need more space. Yeah, well, maybe I'll try putting it in that space over there. Maybe kind of hard to read. So what does this mean? Now we set up and solve the math. So we know that our Ka is 1.8. Is that right? Times 10 to the negative 5. Now we're just putting in numbers and symbols into everything we set up. So instead of just writing the generic Ka or Kc, we'll put the number there. Well, that's going to be equal to x, because that's this concentration, times this concentration, over 1.00 minus x. You know what? Putting the parentheses here might be confusing, because before we put parentheses for non-equilibrium conditions. All I'm doing is putting the parentheses there just to separate these two terms. Okay, so that's going to be equal to 1.8 times 10 to the minus 5th equals x squared over 1.00 minus x. Okay, now, oh, by the way, I'm ignoring units for now. I'm not putting molarities and all that stuff. This is going to confuse things. All right, so you may look at this. We could solve this with the quadratic equation. In fact, I would do that for practice. If you know how to do it, I'm going to actually, oh, you know what? I forgot. I'm looking at my own notes. I'm going to do this two different ways. I'm going to do this with the quadratic equation. If you need a refresher on the quadratic equation, I think the end of your book has some information on it, or you can just Google something. How do you solve the quadratic equation? The difference here is we actually have real numbers. I am going to need some more space. So we need to solve that math. Now I've turned it into a math problem. It's a math problem at this point. So just remember that this is the last step. Okay. Actually, it's going to be nice. I can set this up. There's two different ways I'm going to solve this problem. And maybe I can kind of wing it here with my notes. Oh, you know what? I write this one out in gory detail in case you don't remember the quadratic equation. Okay, so we've got to solve that for x. I'm going to come the whole way over here. So to solve for x, I'm going to take 1.8 and just do the problem. If you know how to solve for x and do it, you can ignore all of this. So stop the video and then fast forward it if you know how to do it. 1.8 times 10 to the minus 5th times 1.00 minus x. I'm just multiplying each side by that to get rid of the denominator term. Equals x squared. So now I'm going to distribute this. So that times 1, that's pretty easy. The units actually would help, but I'm going to ignore those, because this would be units of molarity squared. Minus, this then becomes the coefficient in front of x, which is kind of a weird coefficient. Okay, at this point, it might not be a bad idea to remind you what the quadratic equation is. The quadratic equation is written like this. It's ax squared, so it's the coefficient in front of the x squared term, which we haven't done all of that. Well, there, I guess the coefficient is going to be 1. Plus b times x. It's been a long time since you've done this, just that's okay. Plus c equals 0. Then there's a formula that we use to solve for x for that equation. We're not going to prove the quadratic equation, we're just going to use the formula. But the goal is, we have to get it in this form. It's kind of like y equals mx plus b. You have to get it in that form before you can do anything. So we need ax squared plus bx plus c equals 0. We need to do all of that here. Okay, so what I'm going to do is, let's see. The x squared is here, so I want to bring everything else on the other side. So this is going to be, and see if you can follow me here. I'm just going to write it left to right. So this would be x squared. I'm just going to kind of flip this whole thing around. I've got to bring the other two. This is going to be plus 1.8 times 10 to the minus fifth x minus 1.8 times 10 to the minus 5 with nothing. See what I did? I just so it looks like that. Equals 0. I mean, you could write 0 equals x squared plus this minus that, but it's fine. It's the same thing. Okay. Great. So now we get to apply the quadratic formula. So a equals 1. That's b. And that's c. The negative matters. C is negative 1.8 times 10 to the minus 5. B is positive 1.8 times 10 to the minus 5. Keep track of your units. And you remember the quadratic formula, how you solve it? X equals, let's see what it is. It's negative b plus or minus, which is going to be something we're going to have to think about. Okay. B squared minus 4ac all over 2a. A lot of calculators can actually do that if you put in your a, b, and c, and then hit some formula for quadratic equation. I don't use a calculator like that. But that's the quadratic equation. If you set it up like this is what x equals. And we're only going to use positive roots. So x must be positive when you do all this math. This plus or minus business, whatever gives you the positive root is for x, because x would make no sense to be negative. So x should be positive. And I think that's right. Okay, so let's take this and put it into that. So in this case, x is going to be equal to negative b, so we have to take b and make it negative here. Oh, by the way, I automatically know which root I'm going to take. I think you usually take the positive root. Actually, sometimes you have to think about it. So we're going to have to take the positive root because this can't be negative. So this numerator has to be positive. So we'll take the positive root, and then b squared is 1.8 times 10 to the minus fifth squared minus 4 times a, which is 1, and I don't mean to insult your intelligence if you know how to do this, times negative 1.8 times 10 to the minus 5. So we've got this negative times a negative to deal with, which makes sense because we're up to the square root of a negative number. All divided by 2 times a, which is 1. Okay, you can stop the video here and see if you get the answer. I guess I'm going to show the math a little bit more, but if you want to stop the video and just see if you can do this, ultimately the answer we're going to get, and I'll show some more math, x is going to be, the final answer is 4.2 times 10 to the minus third. And that's going to have units of molarity. So if you want to just stop the video, do that, see if you get that answer, cool, go ahead, stop it, do it. If you want to follow along with a little bit more explicit math, I'll just do a few more steps if you need it. I don't think you need it, but this is a lot more detail than you probably need. So what am I going to do? I'm just going to do every step. So 1.8 times 10 to the minus fifth squared ends up being, I'm going to carry some extra sig figs, 3.24 times 10 to the minus 10th. And that's negative times a negative, so that's going to be plus 7.2 times 10 to the minus 5. All over 2. X equals negative 1.8 times 10 to the minus 5 plus, interestingly enough, when you add these two numbers, you can probably just see this. This is so much smaller than this. 7.2 times 10 to the minus 5. This is negligible. When you add these two together, this doesn't even matter in this case. So you end up getting 7.2 times 10 to the minus 5, which seems weird. That number doesn't even matter. Well, mathematically it doesn't, because it's so small. I just made a mess. Divided by 2. I'm not doing every single step. So you take the square root of this number, add it to this, and you get positive. It has to be positive. 8.5 times 10 to the minus 3 over 2, which gives you that. With sig figs, I just carried 2 sig figs. If you have something slightly different with rounding it, that's fine. Okay, so great, you solve for x. What does that mean? That means that your H plus and your C2H3O2 minus are both the same because they're both x. At equilibrium, those concentrations are 4.3 times 10 to the minus third molarity, because they're equal to x. That's all you have to do for those two. And the concentration of HC2H3O2 equals 1.00 molar initial concentration minus x. I think you can do that math on your own. So you just take 1 minus x and you get 0.996 molarity, which makes complete sense because it doesn't change much from the initial molarity. Okay. The last step, step 4 of that 4-step process is, I'm not going to do that for you. You could recalculate K. In fact, I don't think I have my calculator with me today. Okay. Well, to double check your work, did you do all of this right? We'll recalculate K. Take H plus times C2H3O2 divided by HC2H. So recalculate your K, and does it in fact equal 1.8 times 10 to the minus 5? So does this squared divided by this equal 1.8 times 10 to the minus 5? It should. It should be really close. That way you know you did the problem right. And that's a weak acid. And I think there's one last step on this one. Oh yeah. I think I could fit it in here. So that was part D. That was all part D, wasn't it? Wow. So part D took a long time. Part E, we're just kind of tossing this one in here, is something called percent dissociation. So, percent dissociation is, there's a generic formula for this. It's how much it changes divided by the initial concentration times 100. So how much of it dissociates? How much does it change divided by where it started times 100? So in this case, it changed by 4.2 times 10 to the minus third molarity. It started out at 1.0 molarity times 100, and you'll end up getting, sorry, I keep making that noise, it's annoying, I'm sure. 0.42%. I like calculating percent dissociation because it makes the point. Only point, not 4.2. not 4.2. Only 0.42% of the acetic acid breaks up into H plus and acetate ion. That is a weak acid. HCl, the percent dissociation, would be 100% because all of it dissociates. We wouldn't even do this calculation for that. Okay, I'm going to stop. Well, no, I'm not going to stop the video. That's method 1. That's using the quadratic equation and going through and calculating everything very rigorously. Okay, I don't think there's anything on the next slide. I want to make sure. Ah, yes. I'm going to add this one here. Go to the next slide, so slide 8. And take a look at what's written there. It's called valid shortcut, the 5% rule. So just find that. I'm not going to recopy all of that. So we're doing the hard part. I gave you a hard problem first. This next one's going to look really easy. Okay, the 5% rule. I don't like the word rule here. It's a guideline. So every book calls it 5% rule. And what does it say? For reactions already close to equilibrium, the size of the shift, which is x, the change, c, may be negligible within the limits of sig figs. Okay, well, how do you know that? Well, let's just do an example. Oh, well, I kind of already did the example, actually. So the question is, does the 5% rule does it apply to the example we just did? Could we make an assumption and not have to do all that math? Well, let's see. Well, we already did this one. Is x negligible compared to the initial? Well, we already did that. So what we do is you take your calculator. If x well, we kind of did this, but I'm doing it a little backwards. Just bear with me. That percent ionization is actually this. So we could, x is really, really small. That doesn't really help us with this problem. What I'm going to do is show you how does that apply to math, and how does that assumption make this math much, much easier in some cases. So what we do, we're going to do this a lot actually. Therefore, so remember we had this set up like this before. What we're going to make an assumption here is a couple things. And this does not work for every problem, or we have to do some fancy maneuvering for it to work. 1.8 times 10 to the minus 5 is really, really small. This is a weak acid. X is going to be really small. What we do is we assume that when we do this subtraction, it is so small that we almost don't have to bother with it. So we assume it's not really 0. That's probably a bad thing to put here, actually. It's negligible within the realm of sig figs, within the limitations of sig figs compared to 1. So what we're going to do is we're going to assume that we can do this calculation without the x in the denominator. That math looks a lot easier, doesn't it? You can solve for x there. Go ahead and do it. Well, guess what? You can solve for x. That's pretty easy, isn't it? You just bring this concentration over here. I'm going to put units here to make the point. This is actually a mathematical equation we're going to use a lot. The initial concentration times the Ka or Kb, or for a base, or Kc, it doesn't matter. Square root is equal to x. You're going to see this one over and over again. So I'll write that down actually. So for a lot of weak acids, this is not you'll see this come up again. It's the initial concentration times the Ka square root. Okay, and guess what? Within sig figs, you get the exact same answer for x that we did through the quadratic equation. You'll be expected to do both, because sometimes we can't make that assumption about x. But in this case we can, because x, now typically what you'll do is you'll do the calculation with the assumption. So just to be clear on how you approach these problems. You do the calculation assuming the 5% rule, which means you ignore it in the denominator. Excuse me. You solve for x, then you say, does it meet the 5% rule? So you take x divided by your initial concentration times 100, and if it's less than 5%, you're good to go. And you solve the problem for your equilibrium concentrations. That is the 5% rule, and that's where we are going to end the video.